Up until this point, we've seen equations are a way to indicate that expressions are of equal value. We've even tried to solve a few equations, which means put it in the format, the value of x equals something else. And you may have even seen in class one-step, two-step, maybe even multi-step equations. And we'll start there as well. For example, we have a one-step equation, x plus 5 equals 10. Well, essentially that means there's one step to solve for x in this equation. And that step, in this case, would be to subtract 5 from both sides. And you're probably also familiar that whatever I do on one side of an equation, I have to do the same operation on the other side of the equation. Otherwise, it's no longer an equation. It's not equal anymore. So in this case, I've subtracted 5 from both sides of the equation. And that just leaves me x plus 5 minus 5 is 0 equals 10 minus 5, which is 5. Or expressing it without the 0, x equals 5. In one step, I've solved this equation. And I could do the same with 5x equals 10, but in this case, I'll probably want to divide by the coefficient of x, or multiply by the reciprocal. Either way, it's the same. And the result is 1x, which we don't write the 1 coefficient, we just have to write x, equals 10 divided by 5, or 2. So again, in one step, we've solved that equation for a one-step equation. Let's increase the complexity to a two-step equation. 5x plus 5 equals 10. Well, I'll try a combination of those approaches we just looked at. I'll subtract 5 from both sides to start off to eliminate the constant value that's on the same sides as the x, and that of course becomes 0. 5x plus 0 equals 10 minus 5, or 5. So I have 5x equals 5, and now I'm going to divide by that coefficient, 5, on both sides of the equation, and the result will be 1x, I don't need to write that 1 again, equals 1, and I've solved that equation. And it took two steps, one subtraction, one division. Let's go over and look at y plus 5 divided by 2 equals 10, another two-step equation. Well, in this case, I'm actually going to multiply both sides of the entire equation by 2 to get rid of my fraction or my denominator. So 2 divided by 2 will cancel out to 1, and that will just leave me my numerator, y plus 5 equals 2 times 10 on the other side of the equation, or 20. And now my second step, I'll subtract out the 5, that constant value on the same side as my variable, but I have to do that on the other side of the equation as well. And the result is 5 minus 5 is 0, so I'm just left with y on the left side, and 20 minus 5 equals 15. And I've solved this equation in two steps, y equals 15. Now I can continue even further to multi-step equations. But is it really the complexity of the equation that's the importance, the one-step, two-step, multi-step, how many steps it takes to resolve it? Not really. More important is understanding what processes and types of steps we can take to solve the equation. It helps to understand what exactly are we doing? What is an equation? I like to think of it as transformers. You know, where that car goes through all these complicated steps to transform into this really big, cool fighting robot. Well, it's kind of like an equation, and your job is to transform that big, cool robot back to the original car or the solution. And we can see that with this example. I'll just start with x equals 5, the solution, and I'll work backward for a second. I could add 2 to both sides, and I now have x plus 2 equals 7, an equation, not the solution. I could take that and I might even make it more complex by multiplying by 3 on both sides. And that gives me a new equation, 3x plus 2 equals 21. And then maybe I'll try another operation. I'll divide both sides by 7. And that would in turn give me 3x plus 2 over 7 equals 3. And I might take this another step further and say square both sides. That is, multiply the entire side each by itself. And we know 3 squared on the right side is 9, And the expression on the left side will remain 3x plus 2 over 7 quantity squared equals 9. So now we've got a really pretty good, interesting little complex transformer robot here. And when we talk about solving the equation, we really want to reverse engineer it. We want to undo all the operations we did up to this point that took us from our solution, x equals 5, to our transformer robot. So how do we get back to that simple car, the solution x equals 5? We simply undo the operations. If the last operation was to square both sides, I will probably want to take the square root of both sides. And if before that I divided by 7, then the next step I'll probably multiply by 7 to undo the fractions or denominators that exist there. And then if before that I multiply both sides by 3, I might want to divide by 3 to simplify it and eliminate coefficients. And then I might actually subtract 2 to get rid of any constants on the same side as my x variable that I'm solving for, and ultimately get back to my solution, or in this case, our starting point really, x equals 5. So I like the analogy of transformers. Your essentially equation builds up complexities around the solution, and then your job is to resolve the mystery, which makes solving equations kind of fun. It's like a puzzle. We want to figure out what operation and in what order we can do it to bring back our complicated equation into the simple solution, x equals 5 or something of that sort. Let's take a quick look at what those operations are and in what order we might typically apply them. So one approach we saw is we multiplied both sides. If we had something like x over 4 equals 10, we multiplied both sides by 4. And why 4? Because we wanted to get rid of that denominator. So the 4 divided by 4 cancels out, and the resulting expression on both sides will be void of fractions. There will be no denominator to worry about. Likewise, we also saw addition and subtraction. And when did we deal with that? Well, generally we had x plus 4 equals 10. Our goal is ultimately to isolate x equals something, so we have to get rid of this plus 4 constant on the same side as the x. And in so doing, we subtract 4 from both sides, so that zeroes out and our remainder value is just x. The next operation we would typically look at is division or dividing. And when do we confront that? When we had a coefficient to our variable x that we were solving for. So 5x equals 10, we want to multiply by the reciprocal or divide by that coefficient to make 5x essentially 1x, and we know 1x is really written as x since we don't put a coefficient of 1 in front of it, and in this case that equals 10 divided by 5 or 2. So that pretty much sums up at least our 1, 2, and simple multi-step equations, but is there more to it? And the answer is yes, of course there's more to it. There are many other operations I can do and undo to solve equations. So if I'm presented with the square root of x plus 4 equals the square root of 16, I can attempt to undo my square root or my radical by squaring both sides of the equation. And in this case, the value within the radical becomes the result on the left side of the equation after squaring the square root, and that is true on the right side of the equation as well. I could also have something like 2 to the 5x plus 3 equals 2 to the 10th. Well, I have this base 2 on both sides of the equation and the base exponent relationship as follows. If it's the same base exponent relationship, 2 to the power, then I could eliminate that entirely on both sides of the equation, and my result will be simply the exponents. 5x plus 3 must equal 10 for my original equation to be true. And I can solve for that, again, as a two-step equation. Subtract 3 from both sides. 5x equals 7, divide by 5 on both sides, and we'll simply get x equals 7/5. And I can continue to go with any type of operation I can possibly imagine. The key goal is to figure out what was done in the equation and try and undo that operation to ultimately resolve the equation and solve for the variable we're seeking. Again, this is a fun, creative process, much like solving a puzzle or taking on a challenge. So hopefully you can appreciate that and enjoy the challenge that solving problems can often present. But be careful, you want to avoid some typical mistakes. For example, students often look at the equation 1, 3 quantity x plus 7 equals 10, and they'll try to subtract 7 to eliminate that constant on the same side as the variable x. Well, that makes some sense conceptually. However, the execution is incorrect because remember, according to PEMDAS, we have to evaluate the parentheses first and then do the multiplication by 3 first before adding. So I can't simply subtract 7 and get a result of 3x. That is absolutely not correct. What I'd have to do is evaluate my parentheses and multiply by 3. So I can't simplify x plus 7, not knowing the value of x, but I can multiply through the 3. 3x plus 3 times 7 equals 21. So that becomes 3x plus 21 equals 10. And I'll quickly realize, oops, I don't want to subtract 7. I actually need to subtract 21 to isolate my x on the left side, which will ultimately give me 3x, subtracting 21 on the right side as well, equals minus 11. And I could continue from there. But that would be the correct approach. Likewise, example number 2, x plus y divided by y. Many students will go, oh, I'll just cancel the y's, and that's x plus 1. Well, that's not correct either, because remember, when we have a fraction bar, there are assumed parentheses on top and bottom. PEMDAS says we have to evaluate the parentheses first. We can't simplify the expression in parentheses because they're variables, they're unknown values. So I can't just simply add them like 3 and 5 to get 8. I have to stay with x and y. And I cannot therefore break that apart and divide y by one term of y in that binomial expression of x plus y. I actually have to divide my y by the entire expression in the numerator, which is x plus y. So this expression, unfortunately, cannot be simplified further. It already is in simplest form. And that should also alert students to not try to add, subtract, divide, multiply, or perform an operation on a part of one side. You must perform the operation on the entire side. So one important tip is always plug your results back into the original equation. So if you got an answer that x equals 5 to a problem that said 2x equals 10, you want to plug that 5 back in just to make sure 2 times 5 equals 10. And sure enough, that works. Well, that seems kind of obvious in this case, but when you're solving more complicated equations, there is the opportunity to make a mistake in your calculation somewhere along the lines. This procedure will catch that. There's also the possibility of making a logical error. Remember, equations can have not just one solution, they might have many solutions, sometimes infinite solutions, they're always true, or no solution. By plugging your results back in, you can check whether that could be the case as well. So, one strong word of advice, always check your results back in the original equation.